Welcome to ThirdEye Labs, where we make the unseen seen. Today, the network that learned physics. Start from zero. A partial differential equation is just a local rule. Here is heat on a metal plate. The rule says, every point drifts toward the average of its neighbors. That is all the famous heat equation states. Hot spots bleed into cold spots. Watch the rule run. To compute it, we chop space into a grid, and here is the trap every solver lives in. A coarse grid is fast and wrong. A fine grid is right and brutally slow. Double the resolution in 3 dimensions and time, and the cost multiplies by 16. Now the real pain. Science rarely solves an equation once. Designing one airfoil, forecasting one storm, inverting one oil reservoir means solving the same equation thousands of times with different inputs from scratch, every single time. Imagine a restaurant where every single order means cooking the dish from raw ingredients, from scratch, every time. That is what classical solvers do. Science needs a chef who has learned the dish itself and can plate any variation in seconds. An ordinary network maps a fixed list of numbers to a fixed list of numbers. 784 pixels in, 10 classes out. It is welded to one grid. The paper's idea is bigger. Learn a map between functions. In goes an entire input field, like the permeability of rock, a function of space. Out comes the entire solution field, the pressure, another function. One trained operator solves the whole family of equations, any input, and as we will see, any resolution. And no, it does not memorize answers. It is tested on inputs it has never seen. Zoom into a photo, and it shatters into pixels because a photo stores dots. Zoom into a vector graphic, and it stays perfectly crisp because it stores the rule that draws the shape. An operator is the vector graphic of physics. It stores the rule, not the dots. Here is the bridge between physics and Fourier. Drop a single point of heat on the plate, and the equation answers with a spreading blob, its fundamental solution. For linear physics, the response to any input is just shifted copies of this one ripple added up. That sum is a convolution. And now the theorem this whole paper stands on, one we earned in drawing with math. Convolving in space equals simple multiplication, frequency by frequency in Fourier space. A slow, everywhere to everywhere integral becomes a cheap list of independent multiplications. Drop one stone into a still pond. The ripple pattern that spreads out is the pond's answer to a single point of disturbance. Physicists call it the fundamental solution. Know the ripple, and you can build the response to any splash by adding shifted copies. That is convolution. Now the machine itself, one gear at a time with a real turbulence field flowing through. Gear 1, the FFT. The field becomes its spectrum. The bright center is the big, smooth structure. The dim edges are fine detail. Gear 2, throw almost everything away. Keep only the lowest 12 frequencies per direction, the big circles from drawing with math, and delete the rest. Sounds reckless. Hold that thought. Gear 3, the only learned part. Every surviving frequency gets its OWN small complex matrix R. Not a convolution stencil, a private dial per frequency that reweights it, rotates its phase, and mixes the channels. Then the inverse FFT brings the field home. This is the learned global operator. Every output point felt every input point for the price of a multiplication. Gear 4, a humble local bypass. W multiplies each point on its own, no Fourier involved. It quietly does 2 jobs. It carries the fine local detail the truncation killed, and it tracks non-periodic boundaries that pure Fourier cannot represent. Add both paths, hit them with a nonlinearity, and that, the whole of it, is one Fourier layer. Now resolve the held thought. If every layer keeps only 12 modes, how is the output not hopelessly blurry? Because the nonlinearity between layers mixes frequencies, and mixing recreates high ones. The paper measures it. Truncating the true solution at 20 modes costs 2% error, yet the network, keeping just 12, gets below 1%. The activations regrow the spectrum the truncation deleted. The layers think in broad strokes. The nonlinearity sharpens the picture. A sound engineer does not edit a song sample by sample. They slide the bass up, the hiss down, one slider per frequency band. The Fourier layer is a learned mixing desk for physics, except each slider is a little matrix that can also mix the channels. Assemble it. A pointwise network P lifts the input into a richer channel space. 4 Fourier layers do all the global thinking. A pointwise network Q projects back to the answer. Count what we are training. 12 by 12 modes by 64 by 64 channels complex is roughly 1.2 million parameters per layer. The UNet baseline needs 25 million, and the cost per solve is n log n, the price of an FFT, instead of the n squared of a raw integral operator. Small, global, and fast. Put on reading glasses, and the world gets sharper, but you do not become a different person. Your knowledge does not change with your eyesight. The FNO's weights live in frequency space, so changing the grid resolution is just changing the glasses. The brain stays the same. Now watch the whole machine do a real job, end to end. The use case, forecasting. In goes the state of the flow right now as a function. P lifts it, 4 Fourier layers reason about it globally, Q projects it back, and out comes the flow at a later time. No time stepping, no grid sweeps. An entire forecast is one forward pass through a network, 5 milliseconds. This is what replaced 18 hours of solver time in the paper's inverse problem. And here is why this matters far beyond physics. The paper says it plainly. Operator learning is an image-to-image problem, and the Fourier layer is a drop-in substitute for the convolution layer. Watch the difference. A 3x3 convolution sees only its neighbors, stack layers, and its sight grows just 2 cells at a time. One Fourier layer multiplies in frequency space, so every output pixel sees every input pixel. Immediately, a global receptive field in a single layer, for n log n cost. That is useful anywhere context is global, whether medical imaging, audio, any image-to-image task where far apart pixels matter to each other. 3 places this lands in the toolbox today. 1. ForecastNet runs global weather with Fourier operator layers in seconds. 2. Because the operator is differentiable, you can drop a physics engine inside a training loop and optimize designs by gradient descent, no adjoint solver required. 3. Resolution freedom is a deployment superpower. Train where compute is cheap, deploy at whatever resolution the problem demands, same weights. Keep this layer in your toolbox. Any task where the whole picture matters at once is its home turf. Test 1, Berger's equation. One-dimensional fluid that steepens into a near-discontinuous shock front, the kind of sharp feature Fourier methods supposedly hate. The FNO posts the lowest error of every method tested, 30% below the best prior approach. And here is the headline. Its error stays flat as resolution grows, while the convolutional baselines get worse, because their stencils are welded to the pixels they trained on. Test 3, the boss fight. 2-dimensional turbulence in vorticity form. At viscosity 10 to the -3, the FNO's error is below 1%, half of UNets, with a quarter of the parameters. Honesty beat. Push into the chaotic regime, 10 to the -5, and every method degrades to 15–20%. The FNO wins, but chaos is still chaos. No magic claimed. And the party trick that is actually a theorem. Because the weights live on frequencies, not pixels, the same trained network can be evaluated on a grid 4 times finer than anything it ever saw, in space and in time. To be precise about what this is, the Fourier basis is defined at every point, so the network's answer can be sampled anywhere. It is resolution freedom, not information from nowhere. Now the numbers that made engineers sit up. One solve drops from 2.2 seconds to 5 milliseconds, 1,000-fold. The paper then runs a Bayesian inverse problem, recovering the initial state from sparse late observations, which needs 30,000 solves. 18 hours becomes 2.5 minutes. And being honest about training cost, even after paying 12 hours up front, the FNO finishes first on the very first job, and every job after is nearly free. For the PhD corner, the fine print that makes this a serious paper. Formally, the operator maps between Banach spaces of functions, and training minimizes expected loss over a measure on input functions. Empirical risk minimization lifted to infinite dimensions, where even the existence of minimizers is an open problem, and the authors say so. The weights R carry conjugate symmetry, so outputs stay real. The truncation set is a pragmatic box of modes, chosen to match the FFT's memory layout, not the canonical ball. They tried making R itself a neural network, plain learned weights 1. And the honest limits: the FFT wants uniform grids, periodicity is patched by the bypass, and the mode count is fixed by hand. Each limit seeded a follow-up paper: GeoFNO for geometry, universal approximation theorems for operators, and ForecastNet, which forecasts global weather with this exact architecture. Why did this one architecture start a field? Because amortized physics changes what is affordable. Weather ensembles that took a supercomputer hour run in seconds. Design loops that evaluated one candidate overnight now search thousands. And underneath sits a bigger thesis: convolutional networks own pixel space, transformers own token space, and the FNO stakes a claim that the native space of science is function space, with Fourier as its coordinate system. In drawing with math, circles learn to draw. Today the same circles learned physics. Math can see, now it can predict. In one breath, a PDE is a local rule, and solving it point by point is slow. So learn the operator instead. Function in, function out, free of any grid. The convolution theorem lets it think globally for the price of a multiplication. And 12 modes, one humble bypass, and a nonlinearity are enough to predict turbulence 1,000 times faster than the solver that taught it. In the companion lab, we build the Fourier layer from scratch in NumPy. Read the paper. It earned it. The Fourier layer needs a uniform grid. Next time, the math of learning on graphs, spheres, and curved spaces. Thanks for watching and keep exploring. Next time, beyond the grid. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.